Hello everyone, I'm going to talk to you about Bisers and Trisers. Hopefully you're interested in some of these topics: maths, integers, prime numbers, Fermat's last theorem. If you came here looking for blisters and tristers, then you'd better escape quickly now. So what is a Biser? A Biser is a polynomial of two variables. It's ordered, every term has the same power, and it's symmetrical. And normally we're interested in the sum of the terms. For example, x plus y to the power 4 is this. There are two variables x and y. The powers of x decrease. We've got x power 4, power 3, power 2, power 1, 0. And the powers of y increase. 0, 1, 2, 3, 4. So every term has a total power of 4. Okay. And it is symmetrical. If you swapped x and y for y plus x, it would be the same. So a Biser can be represented by its coefficients like this: 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Same forward and backward, so it's symmetrical. Now Trisers are exactly the same, but with three variables, ordered in a symmetrical triangle. For example, x plus y plus z squared. Get these terms. But when you order them into a triangle like this, first of all the terms with no z, order them like a Biser: x squared plus 2xy plus y squared. And then the z terms, 2xz plus 2yz, and the z squared terms underneath z squared. So every term is a power of 2. And just writing the coefficients like this, see the first term, so this one, x squared is this one. The y powers are increasing from left to right. The z powers are increasing as you go down. And the x powers are increasing from right to left. So this is the x squared term on the top left. X plus y plus z squared can be represented as this in x, y and z. That's a Triser. And note the three-way symmetry. Now, the unit Biser, U neg, as in U negative. You're probably familiar with this kind of expansion. X cubed plus y cubed equals x plus y times x squared minus xy plus y squared, etc. We can show this one here with a sort of long multiplication. I take this term and multiply it by x plus y. So here's the long term multiplied by x, add it to the long term multiplied by y. Here, for example, we have x times x squared, y squared, that's x cubed, y squared, minus y times this, minus x cubed, y squared. So they cancel out. All that's left is x power 5, y times this, plus y power 5. This works for odd powers. So the U neg Biser is like this. Considering just the coefficients, we have 1, 1 minus 1 plus 1, 1 minus 1 plus 1 minus 1 plus 1. That's a uneg 4. So generalizing for n odd, and for now we'll just say x plus y not equal to 0, we have that the uneg Biser for n minus 1 is x to the power n plus y to the power n divided by x plus y. Show an example of long multiplication just using the coefficients. Now the number of terms in a Biser is always the power plus 1. So here we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, starting from 0 up to 8. If we multiply this by x plus y is like 1, 1. So 1, 1 times this, and this gives a total of this. So powers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's x power 9 plus y power 9. All these middle terms cancel out. So x plus y times the uneg 8 Biser just gives you x power 9 plus y power 9, as we would expect from here. Here's an example of evaluating a uneg Biser. For n equals 3, so we have the uneg 2, x equals 4, y equals 7, x squared minus xy plus y squared evaluates to 37. If we use this expression, x cubed plus y cubed over x plus y, that evaluates to 37. Correct. Here's some tables. This is the uneg 2 Biser. So we look up 4 and 7, 4 and 7, there's a value 37. And because it's symmetrical, we look up this way, 4 and 7, 37 again. Uneg 4 Biser, uneg 6 Biser, and so on. Now we're going to apply the Biser a bit to Fermat's last theorem. I'm sure you all know what this is, but in case you don't, according to Fermat's last theorem, there doesn't exist any combination of positive integers x, y, and z and n greater than 2, so that x to the power n plus y to the power n equals z to the power n. We'll call this equation flat. There's another famous equation from Fermat, Fermat's little theorem, flit, that we will use later. So let's say that the imaginary place where solutions to flat do exist is flat Earth. To prove flat, we would have to show that there is absolutely nothing on flat Earth. Of course, we won't totally succeed in that here, but let's try to reduce what could be there to a minimum. Now, if you look up Fermat's last theorem, you'll know that we're only really interested in the cases where x, y, and z have no common factors and where n is a prime number. Any other case can be just reduced to one like this. Okay, so to prove Fermat's last theorem, basically all you need to do is to prove this, because Fermat himself proved it for where n equals 4, and this is all there is that's left to prove, which is quite a lot. Let's look at some inequalities. We know on flat Earth that z is biggest, so let's say x is less than y less than z. x is less than z and y is less than z, you add them together, x plus y must be less than 2z. Also note, x plus y squared, which is this, must be greater than x squared plus y squared, because we're working with positive numbers at the moment. X plus y cubed must be greater than x cubed plus y cubed. So x plus y to the n must be greater than x to the n plus y to the n for n greater than or equal to 2. Now if x to the power n plus y to the power n equals z to the power n, then that means that x plus y to the n must be greater than z to the power n. And therefore z plus y must be greater than z. Now if I put these two things together, this one and this one, we get this. X plus y must lie between z and 2z. So let's try and apply the U-Biser to Fermat's last theorem. We're going to try and prove that z cannot be prime. It's not a lot, but it's a start, isn't it? So, as z must be greater than 2, remember x must be 1 at least, so y must be 2 at least, so z must be greater than 2. We had before this, 2z must be less than z squared, so x plus y must lie between z and z squared. Remember the unique Biser. Rearranging, we have x to the n plus y to the n equals x plus y times the unique Biser. In flat Earth, n is certainly odd, so we can use this Biser. Z to the n equals x to the n plus y to the n. So replacing this with z to the n, we have z to the n must equal x plus y times the unique Biser. We know that this and this are integers, so let's assume that z is prime. Prime numbers cannot be factorized further. So what are the possible values of x plus y and u? X plus y times u Biser must equal z to the power n. Either x plus y is 1 and u is z to the n, or x plus y is z and u is z to the power n minus 1, or x plus y is z squared, etc. Okay, they're the only factorizations possible because we've assumed z is prime. But we've already shown that x plus y lies between z and z squared. It cannot be either of them, it must be between them. So none of these are possible. This is impossible. Therefore, the assumption about z being prime is not possible. Z cannot be prime. Oops. Now we're going to jump ahead to Trisers. An example of what we can do with them here. Now when we're dealing with Trisers on flat Earth, it's easier to use a symmetrical space of x, y and z. Before, we had x to the power n plus y to the power n equals, let's say now, z bar to the power n. We're only considering n prime greater than 2, so n must always be odd. If we let z be negative z bar, then z power n is negative z bar to the power n. So from this we have this, and therefore replacing z bar with z, we have x to the power n plus y to the power n plus z to the power n equals 0. Now we can do maths treating x, y and z symmetrically, though now they can be positive or negative. So this is actually equivalent to the normal way of writing Fermat's last theorem, because n is odd. We're just interested in n odd. Now, I mentioned before Fermat's little theorem. Again, there's a lot of information you can look up about this, some very good YouTube presentations about it. We're considering x to the power n mod n. See these examples. 5 mod 3, that's 5 divided by 3. What's the remainder? The remainder is 2. 5 to the power 3 is 125. Now that's 3 times something plus 2. So the remainder, when you divide it by 3, is 2. 125 mod 3, therefore, is 2. So 5 mod 3 is equal to 5 cubed mod 3. And this is how you write it. 5 is congruent to 5 cubed mod 3. There's another example. 8 mod 5 equals 8 power 5 mod 5. But this example, 6 mod 4 is not equal to 6 power 4 mod 4. So in fact, Fermat's little theorem, FLIT, states for n prime, only for n prime, a mod n is the same as a power n mod n, or a is a power n mod n. Now applying FLIT to flat. On flat Earth we have for n prime this new symmetrical arrangement, but by Fermat's little theorem, for mod n, x to the n is x, y to the n is y, etc. So x power n plus y power n plus z power n, which is 0, is x plus y plus z mod n. X plus y plus z is 0 mod n. Often we're going to use S, as in sum, for x plus y plus z. So we have x plus y plus z equals x, which is 0 mod n on flat Earth. Now, this is a big jump ahead. If you like this video, I can make more videos showing how we get to the T-Triser. Basically, we start with the T-Biser, which uses the U-Biser, and we show the T-Biser has a factor of x plus y, and then when you derive the T-Triser, they all have these 3 factors. So if you want, I'll make another video showing all that, but for now, just to show you what you can do with the T-Triser, I'll just show you the result here. So T means truncated. If you start with the x plus y plus z to the power n, put it in a triangle, you cut off the corners, so it would be like subtracting these terms, that's why we call it truncated. then you can divide it by n times these three terms. For a prime number, you can always divide it by these terms. Now, using Fermat's little theorem, it's quite easy to see why there's a factor of n in here. By Fermat's little theorem, x plus y plus z to the power n must be the same as x plus y plus z mod n, and x power n plus y power n plus z power n must also be the same as x plus y plus z mod n. So this is the same as this mod n. That's why there's a factor of n in this top line. Here's an example. For when n equals 3, you've got x cubed plus y cubed, etc. They'll be taken out, they cancel, x cubed plus y cubed. Then you've got 3x squared y terms, you've got 6xyz. When you divide by n, you'll be left with x squared y terms and 2xyz. And that turns out to be exactly the same as this expression, expanded. So what you're left with is only 1. If you think of the number of terms, you've got 3 terms to the power 3, that's 27 terms, minus 3 terms, that leaves 24 terms. Divide by 3, that's 8 terms, and here you've got 2 times 2 times 2 terms, 8 terms, so this is all that's left. And for n equals 5, the T2 tracer, remember the tracer, T tracer is for n minus 3, so 5 minus 3 is 2. The T2 tracer, 0, 1, 2, this is a power 2 tracer. You get all 1s like that, that's quite nice. So that's x squared plus xy plus y squared plus xz plus yz plus z squared. For n equals 7, the T4 tracer is like this. So the x power is 0, 1, 2, 3, 4. This is x power 4. This is 0, 1, 2. This is 5x squared y, z, etc. For n equals 11, T8 is like that, always symmetrical. I'm going to tell you about a study we did on the values of t mod n. Using a Python program, we found that for values of x, y, z, that is where x plus y plus z is 0 mod n, then the t tracer mod n is never 0 for these prime values of n. Now you might wonder, how can you show that's true for all values of x, y and z? Well, we can use the fact that for any point x, y, z, if you shift it by n, so here x becomes x plus n, the shift will be a multiple of n. So therefore the mod value of this will be the same as the mod value of this. And by symmetry that's of course true in y and z. So the values of t mod n repeat every n for values of x, y or z, just like a recurring decimal. So if we want to investigate all the possible values of the t tracer mod n, we only need to actually look at all the values from 1 to n for each of x, y and z. That's like a cube, n by n by n. And those values repeat for every n. Now on flat Earth, x power n plus y power n plus z power n equals 0. So what does that mean for our T-Tricer? This was our definition. Here we have x power n plus y power n plus z power n, so that becomes 0. X plus y plus z is our s. Y plus z, this is like x plus y plus z minus x. This is s minus x. And this is s minus y. And this is s minus z. Now, remember that s has a factor of n. If x had a factor of n, then s minus x would have a factor of n. And conversely, if x doesn't have a factor of n, then s minus x cannot have a factor of n. So if x, y, z doesn't have a factor of n, then neither does this. Neither does this. Remember we said that x, y and z cannot have common factors, so they can't have any common factors of n. So the only possibilities are either x, y and z have one factor of n, or they have none. So here we're saying if x, y, z have no factors of n, then neither does this. Now what does this tell us? S has a factor of n, so s power n will have a factor of n to the power n. So n to the power n divided by n, clearly this leaves many factors of n. There should be many factors of n in here. If this exists on flat Earth, there would be factors of n in the T-Tricer. But in the real world, it never does, for those values of n listed above. Therefore, using Bisers and Trisers, we can prove Fermat's last theorem for the case where n doesn't divide x, y and z, x, y or z, for these values of n. Now these primes seem to be following a pattern, don't they? But unfortunately that pattern doesn't continue quite as simply as that. So if you like the video, I'll do some more and I'll explore with you what happens after here and what other strange things we can find out using Bisers and Trisers. Thanks very much for watching. Bye bye.